Hi everybody, this is Mrs. Ellsworth, and we're going to be talking about acids and bases. And I'm sorry you're going to have to take notes in your own notebook without note sheets. It's just how it is this day and age right now, so it's how things are with these times. But notice on here that there's lots of cleaners. Cleaners typically tend to be a little bit basic. It means that they're more of a base or alkaline, a base. Foods tend to be a little bit acidic. These are here becoming a stronger acid here, the more sour that it tastes. Okay, this is an antacid, which means a base. It's a very weak base. Anyway, typically we do some exploratory, just going out and inquiring about what is an acid and a base with some typical things. And unfortunately, we got to skip through that. Let me get through here real quick, and we'll get on to properties of acids. Okay, so properties of acids. Acids all contain this H+. Do you remember that we were actually naming acids? It had to have an H on the front of it. And all acids that we talk about here are put into water. And so when you add that H2O to this, you actually get this hydronium ion out of that, the hydronium ion. So acids produce hydrogen ions and hydronium ions. Acids also tend to taste sour. They corrode metal. Being corrosive is one of the big properties that describes what an acid is. Sometimes acids are used to even clean off metals, to clean the rust off of things, clean corrosion off of metals. And then also, the stronger the acid, the higher the electrolyte it is. We'll talk about that in more detail here in just a few moments. Also, acids react with bases to become neutral. They become water and salt water. Okay, a salt. It's not necessarily table salt. Also pHs. The pHs are less than 7. So it goes from, any number less than 7, 6.99999, whatever, all the way down to 0. Those are acids. Okay, and they also turn blue litmus paper to red, and they turn red litmus paper stays red also. And those are typical properties of an acid. Okay, bases. Okay, bases, they produce a hydroxide ion. This is just by one definition. The first one we'll be talking about today. Okay, they taste bitter. They taste chalky. Some of the foods I can think of that have got some taste that is kind of bitter would be, like a Tums that doesn't have any fruit flavoring in it. Those ones have got a chalky flavor to them. They're a little bit basic. And then I was talking about like the skin on the outside of a grape. Okay, that is a little bit basic too. If you open up a walnut, there's this piece that's in between the two walnut halves, and if you get that in your mouth, that's very, very bitter. And if you've ever had soap put in your mouth, that's very bitter too. Bitter is not something that we look forward to tasting. I know that some things like kale is also basic, and same with some legumes. Those are type of beans. And so those things are bitter. There's just not a whole lot of things that we go out and seeking that are bitter flavored. Okay, and they also have electrolytes too. The stronger the base, the higher the electrolyte, and we'll be talking about that in a little bit. Now, if you put acid in your hand from the slide before, acid, it just feels like it's wet. Okay, if it's a really strong acid, of course, it's going to start stinging you a little bit. But bases all feel slippery. Okay, just like acids react with bases to form neutral, so does bases. Bases react with acids, that's kind of the backwards part of it, to form water or neutral and salt, right? And then also these pHs are greater than 7. Even like our blood, that's like 7.4 something, that is typically just slightly basic, a little bit of a base. Okay, and then this one here, when we talk about litmus paper, it turns red litmus paper blue, and blue stays blue. Okay, let's do a little bit of reminding of how we name those acids. If you remember right, we had that table. If it's an 8, it's an icky. If you ate something icky, that's how I always remembered it from my teacher. So if your ion ends in an 8, it's going to be an ick acid. If it ends in an ide, this is just a plain atom ion on the periodic table, it's going to be a hydroic acid. If it ends in an ite, like chlorite, is going to be an us acid, like chlorous acid. Okay, let's see if you remember some of that. So take out your purple sheet and name these 3 right here. Okay, so pause it and name them, please. Practice. Okay, here we go. So HBr is just hydrobromic acid, because that's bromide, so it goes in the hydroic acid. Okay, this right here is carbonate, so it's just going to be an ic acid. This is sulfite, so it's going to be a sulfous acid. Okay, now let's challenge ourselves. We might have some memorized already because these are typical ones that we use. Hello, there we go. So name these acids. Pause it, and then I will give you the answers when you restart it. Okay, the first one is hydroiodic acid, hydrochloric acid, sulfuric acid. Sulfuric acid is used in a lot of products. A lot of industrialized things use sulfuric acid. Nitric acid, same goes there. Nitric acid. And oops, this needs to have a 3 here. This right here would be phosphoric acid. Okay, some common bases. Sodium hydroxide would be one. Potassium hydroxide would be another. Barium hydroxide. Are you seeing something that's familiar in each one of these? Same with magnesium hydroxide. These all have a hydroxide in them, and by the Arrheniius definition, which we're going to go through here in just a little bit, these ones are, whenever it's got hydroxide in it, is showing that it is a base. Oh, I have one more, aluminum hydroxide. Okay, so acids and bases were typically thought to be about how many oxygens are on it. Okay, and so then they later on discovered that an acid, the important part about an acid is that it had an H on it. And so, but that's not always true, because I mean, some things have lots of H's on it. I mean, why is a CH4 instead of H4C? But this one here is clearly neutral if you're ever going to take its pH. And so there's some definitions, and the Arrhenius definition is the one we kind of were just talking about. Starts with an H, ends in an OH. That is typically what that described. So with acids and bases, this here was revolutionary from a long time ago when they started testing these. And anyway, so this guy, he discovered that it was actually because they had this hydronium ion on it. The hydronium ion is the hydrogen ion. It's in water, so you add the two together and you're going to get hydronium. And he found that in our Arrhenius definition of an acid was that they produce these ions when they are placed in water. So they have those ions when they're in water. And bases, typically, they are found to have hydroxide ions when they're in water. Now, not all these work perfectly like that. So if you look at hydrochloric acid, okay, and we're going to put it in water. Okay, then what happens is that hydrogen ion just gets attracted to the water and it produces a hydronium ion. So that's what the hydronium ion looks like. Perhaps you should write that down next to that. It produces that hydronium ion in water, and then there's still left over an ion in there. What would that be? The chloride ion. Okay, but this is the part that does the reacting, that has the properties of acids. Okay. Now the Bronsted-Lowry is another definition of acids and bases. This one is just, he typically says that, hey, acids have got that proton on them. How did they get a proton on this? Well, right here is a hydrogen atom. Okay, and inside the hydrogen atom, if you look on your periodic table, it has got one proton in the center. It has no neutrons when we do our Bohr model, and it's got one electron hanging out there. And so what happens in acids is that it is an ion, so it's going to lose that. So all it has left is just one proton in the center. So that H plus that you see on the front of your acids is actually a proton. That's all it is. There is no electron, and there never was a neutron in the hydrogen ion. Okay, so it's a proton donors, able to go out there and donate them to reaction. Bases, however, are proton acceptors. They're going to take it in. And so this proton is really what the definition is of the Bronsted-Lowry definition of an acid or a base. So our first definition was the Arrheniius one. Okay, the second one is Bronsted-Lowry. And these are just very simplified ideas of what their definitions of acids and bases are. Okay, so now we're going to look at electrolytes, because amphoteric, there's a term that you need to write down. Amphoteric is a substance that behaves as an acid or a base. Okay, and in electrolytes, this is a great way of showing this idea. So let me pause this here. Okay, here we've got a demonstration on a simulation by PhET Labs, and it's demonstrating what an electrolyte is. Okay, and there's just a few different things that we're going to do. We're just going to test these ones right here, and we're going to decide whether it is a strong electrolyte or not. And to be an electrolyte, it conducts electricity. It conducts electricity through whatever solution that it is. Okay, so in this case right here, we're going to go with water, and let's put in all this solvent in there, all the waters, all those gray molecules. Okay, there's very few water molecules that bounced into each other, and so they've created some ions in there. There's very few of them. Okay, and I don't know if you can see it on this video, but there's very little amount of light coming out of that. In fact, this is so little that in my classroom, when we do the light bulb demonstration with this, you did it in 9th grade also, when we do the light bulb demonstration of this, we don't even see it. Okay, then we'll go to a weak acid. Now we've got more light coming out of this. Okay, notice that we have more ions. So here are acid ions, the hydronium ions, and here are some hydroxide ions. And these are here some acid ions. But you'll typically see that this is talking about, in this acid right here, notice that there are still lots of them that are in molecule form. Okay? There are very few ions. The ions are showed with the colorful ones. Okay? Very few ions, and that's why this right here does not have much brightness. Okay? Then we'll go to a strong acid. Wow! Look at all the ions in there. Again, the ions that are producing the ions that are helping this produce electricity, there are so many of them in there now that we have a very bright light. Okay, let's look at a weak base. Hey, is that much different? Okay, so here's our bases that we have in here, and they're still staying together as a molecule, but then some of them do go and break into ions. Here is the hydroxide ion here, the blue ones are, and then I can't quite see what the red ones are. It's part of the base ion, and so those ones are still ions of a base. Again, this is in a whole bunch of water, and so you'll notice there are not a whole ton of ions in here, the colorful ones, and that's why it is not lighting up. So let's look at a strong base. Okay, very strong. Lots of ions in here. Look at all those base ions. Okay, and so we've got tons of base ions in there that are conducting electricity. In fact, let's even compare a strong acid to a strong base. Okay, it looks the same for the strengths here, and it looks the same for just different colored ions there, but it has really got a lot of them in there compared to others. Weak acid looks pretty similar. Okay, just different ions. Again, the gray ones are not conducting electricity because they are a full molecule. It's the ions that conduct electricity. Tomorrow I'll be asking you a question right away at the beginning of the day to have you check in with me, and I'll be asking you a question about what makes the light really bright, dim, or not turning on, or just barely turning on. What is happening inside the solution? And so I'll try and figure out an easy question, and you keep it simple. Okay, and it's going to be about that so that you can help describe it. So just keep it simple in a couple of sentences worth. Okay, I'll see you online. Bye-bye.